Welcome to episode 7 of Tracker for Beginners. Today what I want to look at is how we handle objects moving in 2 dimensions. So far everything we've done has been objects moving in either the x-axis or the y-axis. Now I want to look at things like this airplane here that move in both the x direction and the y direction. And I've gone ahead and given our airplane the name Dawn the Airplane, named after one of our Patreon supporters, Dawn. Thank you, Dawn. To our other viewers, if you're interested in supporting this channel, you can see the links in the description below. This is a video I took while I had a 13-hour layover at an airport that shall go unnamed with an airline that shall go unnamed, but I had nothing better to do, so I just took footage of airplanes taking off. I was pretty happy with this thing taking off, so I want to use this airplane as an example of how we can track 2-dimensional motion. So I have no idea what the mass is of this airplane. I have no idea what the scale is because obviously I couldn't go out to the runway to put a meter stick right underneath the airplane. So we're just going to use this. We're going to take this data qualitatively, right? Because we want to learn how to create and analyze the data. I don't really care what the actual numbers are. So just don't worry about the numbers on any of this stuff. We're just looking at how the software works. So as a recap, I first need to auto track this airplane. Let's try to grab Shift Control click. I need to grab something just on the airplane because this background is going to change because of all these clouds. Let's go ahead and shrink this down a little bit so to look for these little lights on the airplane there. And let's click on search. And as always, you want to keep an eye on the object you're tracking here and keep an eye on the template and the match. So you want the dots to follow the thing you're interested in, and you want the template and match to stay a pretty good match with each other consistently. And I think that's working out pretty well. So far, so good. We are almost at the edge of the frame. There we go. Okay, great. So now that I've got this thing moving in 2 dimensions, I've got a couple of different things to keep track of. I've got the position to keep track of, but I want to look at the position along the x-axis, and I want to look at the position along the y-axis. So the first thing I can do is look at x versus t. So this is giving me the horizontal position versus time. This graph doesn't care anything about how far up and down it goes. This is just the distance along the x-axis here. And in fact, what you can do if you move this axis, if I move this thing to the left and right, you can see my x values here on the vertical axis change, right? So if I move this thing to the right a little bit, then the plane gets closer to 0, so my 0 actually appears here. If you want to, you can adjust this, this axis left and right until you get the x motion to start at 0. So another way to do that would be to go back to the first frame and just put the vertical axis going straight through there so that this point here where the plane starts is 0. That's not necessary, but it's kind of nice. It might make your data fits a little bit easier later. Then I can do the same thing with the y. So when I want to look at the y position, I just click over here, y, position y component. And this gives me the vertical position of the plane. Again, there's nothing, these numbers are not really in meters, these are just in fake units. And you notice again, this thing doesn't start at 0 because I haven't moved this thing up and down. So let's actually take this crosshairs and try to pin that right on the starting point of the airplane right there. There we go. So that's probably as good as I'm going to get that. I'm sure there'll be someone who leaves a comment telling me that there's a way I can automatically do that. Thank you for your contribution to the viewer's education. And so now what I can watch, I can click play and I can watch the thing take off vertically. So this is its vertical position. And then I can watch the thing take off horizontally. I can watch the horizontal position. And what I notice is that both of these have a pretty good parabolic shape, approximately. So in other words, it is getting faster in the x direction and it is getting faster in the y direction because both the graphs are getting steeper, and the steepness of the curve tells you how fast the thing is moving. Now I can also have Tracker tell me that steepness. I can have it tell me the velocity. So when I come down here, I can look at the velocity x component. So here we're looking at the x component of the velocity as we go along, and this thing actually has a decent curve to it. So that tells me that the force acting on this airplane is not constant, which is what I would expect, knowing about airplanes, right? The thrust is not necessarily constant while you're taking off. The drag and lift are certainly not constant while you're taking off. So let's look at the Y component here. Y is a little bit curvy too. You notice we've got this jumping up and down a little bit. That's not because the plane is lurching forward and then slowing down. That's just the messiness in the data, right? That's the messiness in my video and in how well this thing is able to track these. So don't take the up and down as being significant. Just look at the overall shape of the Y velocity here. Now you might also be thinking, well, that tells me how fast it's rising. This thing, the Vx, tells me how fast it's moving forward. And of course, there's a teensy bit of forward motion that we're not capturing because this plane is heading toward us just a little bit. So we're not going to, we're having to ignore that because the tracker can't capture forward and backward motion. They can only capture right and left and up and down. But this is decent enough to look at. But you might be wondering, well, how fast is the plane going, period? Like if I'm on the plane, how fast do I feel myself going? Well, I'm glad you asked that because you can click on this. Your third option is the velocity magnitude. So magnitude is where you have a vector, right? So this velocity we're looking at is a vector. It has a horizontal component and a vertical component. And if you think of that vector in terms of having a horizontal component and a vertical component, you can think of it as forming a right triangle. So the Vx component goes on this side. The Vy component goes on this side. The V, the total, is then the hypotenuse. So you just take Vx squared plus Vy squared. So all Tracker is doing is for each of these data points takes Vx squared plus Vy squared, take the square root of that, you have the magnitude here. So this gives you an idea of how the magnitude of the velocity is behaving. And so you get a pretty neat graph here. You get this increasing here. Now, of course, also vectors have a direction. They have a magnitude and a direction. So another thing you can look at is the velocity angle. So this is going to show us what direction the velocity is pointing in. So this is the theta v. It looks like it's measured in degrees, I'm guessing, from the numbers here. I'll need to look that up to confirm it, but I believe that's going to be in degrees. I don't see why you would have 23 radians or something. So anyway, it looks like this is averaging out to about 25 degrees. And in fact, if you look at the angle here, so we always measure our angles from the positive x-axis, that means if I rotate up this way, the plane is taking off at about a 25 degree angle. And that looks about right. I think we can confirm that if I go to Create, Measuring Tool, and then Protractor. So if I drag my protractor over here. Let's see, I can drag this point. Let's put this point at the origin here. Let's take this point over here along the horizontal axis, and let's take this point that up to up along the direction the plane is pointing. Yeah, I get about a 25 degree angle here. You can't see it because of the axes. Yeah, I get a 25 degree angle there. So let's go back to Don the airplane. We're looking at theta v. So yeah, okay, so that is in degrees. Okay, that's good to know. Yeah, we're physicists. We like degrees most of the time. Cool, so I've got a 25 degree angle there. So, and that actually shows me that the plane's angle is pretty consistent. Again, there's a lot of jumping up and down because of the variation in the placement of the data points. But if you actually look at the scale here, it's all within, a few degrees of each other. So let's actually zoom this out between, let's say, 0 and, oh, excuse me, that was the time, not the, between 0, there we go, and let's say 45 degrees. Yeah, this thing is pretty consistently around 25 degrees. So even though the plane is speeding up, it's keeping its direction pretty consistent, right? So a vector has a magnitude and a direction, so this tells me that the magnitude is increasing, but the direction is staying pretty steady. Now, one other neat thing I can do with Don the airplane here is I can take my axes, I can change both these axes. There's no reason you have to have time on the horizontal axis, except that we usually consider time to be the independent variable, but I can make this horizontal axis anything I want. So for example, I can make this the x position. I can make this the x component. So here I've got the y component versus the x component. I've taken time out of the picture entirely. Basically, time is just indicated by the progression of the dots here. And what I want you to notice is, let's play the video again. As I move along here, this graph now, the y versus x, is following the dots here in the video, their vertical component versus their horizontal component. So this is giving me the trajectory of y versus x. And this is showing me that the angle is pretty consistent. So even though it's speeding up in the y and speeding up in the x, that speed up in the y and speed up in the x, the accelerations there are matching each other pretty well to where I end up with a decently straight line, right? This is what I, as a passenger on that plane, if I were able to take off at that point, this is where I, as the passenger, would want to be traveling. I would like to be traveling at a pretty consistent angle as I'm speeding up. So this is pretty cool. This, if you graph y versus x, you can get the trajectory of the plane. The second example I'd like to give you of tracking things in 2 dimensions is this neat little merry-go-round thing that my wife and I found at Mandarin Park here in Jacksonville. You can't quite tell from the video, but this thing is tilted. So the legs in the back here are taller than the legs in the front, which means that a child can grab onto this thing and then ride it around, and they're going around and vertically up and down. So I held my camera up as high as I could to get this thing head on. It's still a little bit foreshortened here, but I thought this would make a neat tracker video. We're looking right now at the X position of the little green band here. The dot on the green band shifts around a little bit. That's why there's a little kink here and a kink here, but I'm not too worried about that. And you can see that the thing is going faster at the beginning and then starts to slow down under the influence of the friction. So this is the X position as it goes around. Again, I can look at anything I want to. I can look at the Y position. So this is how far vertically it goes. It's going to have a similar graph. It just starts at a different point. But what I want to use this to show you is some of these other variables that you can look at. For example, there's the position magnitude. So we saw the velocity magnitude before. Now let's look at the position magnitude. And this thing is going all over the place because I haven't set up my axes yet. So last time I wanted this to be at the starting point of the airplane's motion. Now what I want to do is I want to put this as close to the center of this circle as I can. So what I'm going to do is try to put the thing in the center. So I wanted to go from the lowest point down here to the highest point up here. I think I've got that probably good. And then I want it to go from the farthest left point to the farthest right point. I think that needs to come up just a little bit. Okay, cool. And again, the scale here doesn't really matter. I think this thing was maybe like a couple meters wide or something. I don't know. So we won't worry about the actual numbers here. But what I want to do is look at the position magnitude. So now that we're measuring from the center here, this x coordinate, this is the horizontal distance from this point to the point we're going out to. So if I start this thing, for example, at the beginning, my green bar starts over here, so I have a negative x coordinate. And then when my wife pushes it here, right when I get to about here is where the x should be at a maximum. Sure enough, the x is at a maximum here. Then I have to let it continue until about this point here. This is where I'm at the y-axis, so my x value should be 0. Sure enough, my x value is 0 here. And then you can do the same thing with the y. It goes from right now the y is at a maximum. If I let it continue, when it gets to this point, the y will go to 0. Sure enough, right there, the y goes to 0. So this is a really neat example of rotational motion. So if you had trouble learning the unit circle in high school or whenever it is you learn the unit circle, this is a good example of kind of getting that addressed in your mind. But if I go to the position magnitude, right, position magnitude here is going to be the x component squared plus the y component squared. Well, this thing is in principle a circle. It's not being represented as a circle in the video because I'm recording this at a little bit of an angle, so it's a little bit foreshortened. But if I take this thing, let's take our minimum value down to 0, as you do, then what I can see is that the position magnitude is oscillating around a constant value. And if I were to get higher, if I were a little bit taller, then I could view this thing head on. This position magnitude would be a constant. It would be the radius of the circle. So this is a pretty good approximation of constant. I mean, it's oscillating up and down a little bit. But the other neat thing I can do is I'm looking at basically the radius of each point, or the distance between each of these points and the center. I can also look at the angle that each of those points sits at. So let's go over to our position angle here. So now what you can watch, let's see, right now we're at this point over here. This point is pi radians away. So if you look at this, we're jumping from pi to negative pi. I'm not sure why some of Tracker's variables are in, or some of their angles are in degrees and some of them are in in radians. I'm not sure why, because if I click and go down to the rotation angle, now this thing is in degrees. Then right now it's going up to 180 degrees and 0 degrees. I'm not sure why this data is so much messier than the position angle. I'll need to learn a little bit more about what each of those means. But basically, this is the angle that if you draw a line from the center point to the dot here, that's the angle that it makes, measured from the x-axis. So we're coming up around here. It's going to approach but not quite reach the x-axis, so we're approaching 0 over here. And you can kind of get an idea of how fast the thing is spinning from this graph too, right? Because if I go to the beginning, let's go to the beginning of the video here, the thing is moving fast. There's a lot of space between the points, and my graph is quite steep. But then my graph is getting shallower as I go around because the thing is slowing down, so there's less distance between the data points. And so as we wrap around the pi, negative pi barrier here, we're coming around to negative pi over 2, the thing is definitely slowing down, right? It's getting shallower. Well, I can also look at that by coming down here to the angular velocity. So this thing omega, this is how fast the thing is spinning around. So when I look at this, I see a definite decrease to it. Again, there's a little bit of lumping going on here where it looks like it's speeding up, but again, that's because we're looking at this thing at an angle. But really what's happening is the thing is slowing down as it moves around. And so here I've got the angular velocity, the degrees per second in this case, as this thing slows down, which is pretty cool. Now again, a lot of this is messy because of the angle that I'm shooting at. So here is an offer for my students who have made it this far in the video. If you go to Mandarin Park and find this thing on the playground, I don't know what it's called, this merry-go-round, whatever it is, and you video it from just the right angle, right? So perpendicular to the plane of the circle so that it makes a circle in the video and you get a nice consistent decrease there. You do that for your activity for this week, and we will get you some extra credit for that. That is an offer to my students. Let me show you one other neat thing you can do with this. Again, remember, you don't have to graph everything versus time. So like I can graph the velocity x component versus something else. I can graph that versus the velocity y component. Watch this. This is going to be really cool. What I get is this neat spiral. So what I'm looking at right now is velocity space. So just ignore all these little data points over here. That's just the video messing up. But what I get is this spiral going in. This is the horizontal velocity versus the vertical velocity. So like, for example, when we get to this point right here, we're at 0x velocity because the thing is heading only upward. It's not heading to the left or the right. So we get 0x velocity, but we get a pretty decent y velocity. But as it continues, when I get to the upper point here, waiting for the upper point, oops, there we go. So when I get to this point here, we're at 0 y velocity. But you notice as I continue along, this trail spirals inward because I keep losing speed. I keep losing magnitude. So the magnitude is the distance from 0 to each point. So as the thing spins around, I'm losing speed. So I'm falling in on this spiral in this velocity space. So we call this kind of graph a phase space plot. This is another way of looking at your data. It's really cool. It's a lot of fun to work with. So anytime you have two-dimensional data, try looking at the velocity components versus each other, and you can get an idea of what the phase space plot looks like. Okay, so this was a lot of fun looking at a couple things in 2 dimensions. I hope you have just as much fun working with your two-dimensional problems. As always, thank you so much for watching. I will see you next time. Bye-bye.